Hi everybody, my name is Cameron and today we're going to be looking at electric circuits. We're going to be looking at the symbols that we use when we draw electric circuits. We're going to be looking at simple and parallel circuits as well as Ohm's law. So let's start with what a charge is. Okay, so we know that atoms are made up of positively charged protons, negatively charged electrons, and neutrally charged neutrons. Okay, so when there is a equal amount of positive and negative charges in an atom, we say that that atom is neutral. It has no charge. Okay, but if that atom were to lose or gain electrons, it becomes charged and we call it an ion. Okay, so you get positively charged ions when it has lost an electron because there are more positive protons, and we get negatively charged ions when they have gained an electron and there are more electrons than there are protons. Okay, now it's important to know that the number of protons doesn't change because your element isn't changing. If that were the case, then maybe our copper wire would be changing into another element all the time. Okay, but it doesn't. It's just the movement of electrons that gives an atom charge. Okay. Now, when an object builds up a charge, okay, it is going to form a non-contact force called a field or an electric field. Okay, and this electric field is obviously going to act like a sort of magnet in a way that like charges repel like charges and opposite charges attract one another. Okay, so in this diagram here, we can see that the field lines move away from a positively charged object, okay, or a positively charged atom, and towards negatively charged atoms. Okay, so when we're looking at electric current now, so we know that charge is generated by adding or subtracting electrons from an atom, okay, giving it a charge. But what about those electrons is going to create electrical current? Okay. Think about current as the flow of those electrons. Okay, so current is the flow of charge through a conductor. We talked about this in a previous lesson. Conductors are things that are able to transmit either electrons or heat well. Okay, so you can think of current as the current in an ocean. Okay, it's that force that is moving the water. The water itself isn't the current, right? It is the force that moves the water. The water can be the electrons, let's say, and the current is the force behind them moving. Now, these conductors that we were talking about are also referred to as circuits. Okay, and when we talk about circuits, it's the push of electrons through a conductor through various components. Okay, and the source of these electrons isn't just the metal, but rather a battery. Okay, that battery is going to provide the electrons required to move through the circuit, usually to specific components. Okay, and those components are going to be represented by specific symbols, and these are universal symbols. So someone from Japan can talk to someone from Jamaica, let's say, an electrician. Okay, they can get together, share their diagrams, and both of them are going to understand exactly what components are being used in this electric circuit. Pretty smart. So just some of the symbols that would be important to know. Any of the lines are going to just represent your wire. Okay, a cell or battery is going to be represented by these two lines. Okay, the positive side is the longer line, the negative side of the battery is the shorter line. I like to remember this by thinking, well, a positive has a lot more lines than just a negative. So the positive side is going to have a longer line. Okay, so one cell, okay, is two of those lines. We call it a battery usually when it has multiple cells together. Okay, then resistors can either be a sort of square like this, okay, and that means that it can represent various resistors. But something like a light bulb, okay, will also be considered a resistor, but we use a different symbol for it. It's that circle with an X. Okay. Then obviously we're going to be using our voltmeter and ammeters, okay, but we'll get to that later. A switch, as you can see here, this would be an open switch. As soon as we connect those two dots, it would be considered a closed switch. Then we have a variable resistor. Variable resistor just has a line through it. That means we can change the resistance. Okay. And those would probably be the main ones that you would have to know right now. Although it is a good idea just to go through them and familiarize yourself with some of the symbols. Another one that we would need to look at, and I think we do in the next one, is a diode, which is over here. Okay. So the first is a diode. Okay. The diode is this specific arrow because it shows which direction the current should be flowing through it. Okay, if it follows in the forward direction, okay, that means the resistance is going to be quite low. Okay, reverse direction and the resistance is going to be very high. Okay, so an example of this is a light emitting diode, an LED. Okay, we know that LEDs are very energy efficient, and that's because they have a very low resistance if the current is going in the right direction. This is what we call a non-ohmic conductor. Okay, and a non-ohmic conductor means that it doesn't follow Ohm's law. That's something we'll get into soon. Okay, a thermistor is usually something that can be used on kettles. Okay, so if you've ever noticed you put a kettle on, it's going to turn off when the water starts to boil. But how does it know? It's going to be using a thermistor. A thermistor it's a variable resistor. Okay, so the resistance is going to decrease as the temperature increases. At some point, that resistance is going to be so low, it's going to flick a switch, or the current can be sent through it. It's going to flick a switch and the kettle is going to go off. Okay, but as the temperature decreases, the resistance is going to increase. Okay, so that you can put your kettle back on when the water's low. Okay, have a look at this. Next time you boil the kettle and it flicks up, you can't put it back down, or it won't go down for long. Okay, only until that that thermistor has cooled off will you be able to put it back on, because the resistance is so high that it cannot have current going through it to turn it off. Okay. Another example is a light dependent resistor, where the resistance is going to decrease if light intensity increases, and vice versa. So we've talked about charge being the force behind the pushing of an electric current. Okay, sorry. Current being the force behind that is pushing electrons through a conductor. Okay, a charge is when something has more or less electrons. Okay, the current is what's pushing it through. Now we're going to be looking at voltage. Now, voltage is the measure of energy or work done as the charge moves between 2 points. Okay, so voltage or potential difference, the difference between 2 points, is going to equal to the energy divided by the charge. Okay, energy measured in joules, we covered this in a previous lesson, and charge measured in coulombs. Okay, this is where we come to Ohm's law. Ohm's law, that resistance, okay, is going to equal to the potential difference divided by the current, your volts over your amperes. Okay, and that means that your voltage is directly proportional to the current passing through those 2 points. Okay, so resistance is also measured in ohms. That's that weird funny symbol over there. And we've talked before about the fact that resistance is going to be kind of like a frictional force. Okay, we can find this resistance in wiring as well. Okay, so it's anything that will resist the passage or the movement of electrons through our circuit. We call it a resistor. Okay, and the resistor is going to limit the amount of current that is given to a circuit. Okay, if we had to move this calculation around, okay, and if we had to put current as our topic of the equation, okay, current would equal to potential difference divided by resistance. So if that resistance increases, our current is going to decrease. So let's look at the different types of circuits. We have series and parallel. Okay, so when something is in series, that means that the components are sitting one after the other on the same sort of wire, on the same line. Okay, in this case, your current is going to be the same for all the components. Okay, but your potential difference is going to be shared equally between all three. Okay, and to work out your total resistance, you're just going to be adding up all the resistances all the ohms of each resistor on that line, and that's going to equal to your total resistance. Okay. Whereas in a parallel circuit, our total current is going to be the sum of the current from each branch. So notice that now they're not all on the same line, they're going to be separated on these branches. Okay, so we have to add up the currents of each branch. That's going to equal our total current. The potential difference is going to be the same for each branch now. Okay, so in series it would have to be shared, but in parallel it's going to be the same for each branch, and our total resistance is less than the resistance of each branch. Okay, so we have to find the total resistance by going 1 divided by the resistance of each resistor, okay, and then that to the power of -1. And it's important to know that your cells can also be in series or in parallel. So here's an example of a series circuit. Okay, in this case, we're going to have 12 ampere provided by the circuit, as well as at 20 volts. Okay, so the current is going to be the same for all of them. They're all going to be at 12 ampere current because it's in series. Okay, now the voltage, however, is going to be firstly 20. Okay, and then what you're going to have to you're going to have to figure out the voltage for each resistor. Okay, and then you're just going to minus them. Okay, so it's going to be 20 minus 3 minus 1 minus 2 minus 5. Okay, and that is going to be our total voltage is 9 at the end. Okay, and then calculating the total resistance, we're just going to add up the resistances of each resistor. Okay, because it's all in series. And if we would say a circuit with a voltage of 25 volts and a current of 5 ampere, we're just going to put it in our Ohm's law equation, and that is going to give us a resistance of 5 ohms. Now in a parallel circuit, however, our current is going to be split up equally between each branch. Okay, so it's 3 ampere per branch. Our voltage is going to be the same for each branch, regardless of how many resistors there are. Okay, except for this one, as you can see, it's 7.5, 7.5, because they are in series, but together they are still 15 volts. Okay, and then calculating the total resistance is going to be just 1 over each resistance and the sum of that. Okay, so let's talk about static electricity. So we've all been shocked. I'm sure in some time in our life we've touched a piece of metal, or maybe we've touched someone else, and you shock each other. Okay, now we know that is static electricity, but what actually is that? Static electricity is when an object becomes charged, okay, meaning that it either needs to gain or it needs to release electrons, and then it touches something else, and those electrons quickly jump from one object to another. Okay, and that is going to be this static electricity. Now, creating static is usually done through friction. Okay, so if we take the balloon in hair, we know that. Okay, if you take a balloon and you rub it on your head, what is happening is all the electrons from your hair are being transferred to the balloon. The balloon becomes negatively charged, your hair becomes positively charged. Opposite forces are going to attract one another, and your hair is going to stick to the balloon, or that balloon is going to stick to another object. And remember, once something has gained a charge, it is going to have these electric field lines. The further away from them you go, the less strong the field lines. Okay. Now, a Van der Graaf generator works in a similar way. Okay, and what that is going to do is generate a positive sphere, and that's going to sometimes have an oppositely charged stick or another ball. And what you can do is come in close contact with that, and you'll see a spark jump from one to the other. Okay, so we know that Ohm's law states that voltage is directly proportional to current and current to voltage. Okay, as long as the temperature remains constant. So temperature plays an effect on the movement of electrons. Okay, the higher the temperature, the more resistance there will be to the movement of electrons. Okay, that's why a lot of gaming computers will have intense cooling systems. And if a computer overheats or if your phone overheats, it shuts down. Okay, because the resistance in the cabling becomes too high. So an ohmic conductor is a conductor that obeys Ohm's law, so the temperature has to remain constant. Okay, resistance is going to be 1 divided by the gradient, okay, of our graph, which is equal to 1 over your current divided by your volts. It's perfect or an ideal resistor, okay, and reversing the current is also obviously going to reverse the voltage. Okay, this was like the series and parallel circuits that we were looking at earlier. Okay, these are ohmic conductors. But a non-ohmic conductor, the temperature does not remain constant, so voltage and current are not going to be directly proportional. Okay, resistance is going to increase as the current increases and the temperature increases, resulting in the electrons traveling faster, but in a more random direction. It can be going both ways, you see that. And the voltage is therefore not proportional. So this is the graph of a non-ohmic conductor. Then we finally get a diode. Now diodes limit the current to flow in one direction, we said. Okay, so as soon as the current starts flowing in the opposite direction, the current is going to be zero because it has a very high resistance if the current is flowing in the opposite direction. It's just going to stop it. Okay, so when it comes to types of resistors, we've been through this. The light-dependent resistor as well as the thermistor. The reason they're used is because their resistance is going to change depending on outside stimuli, either through light or by heat. Okay. Now another one that we can have is a variable resistor. Okay. Now if you in your house have lights that you can dim, okay, or make brighter, as well as the volume, let's say, that's going to be variable resistors, where we control how much resistance it is going to give to the current, and therefore what the current is going to be when going to the lights, let's say. Okay. Yeah. So my name's Cameron, and this has been Electric Circuits. I will see you in the next lesson.